In this video we're going to start looking at Bode plots now. All a Bode plot is a magnitude and a phase plot of a complex signal. So this will become apparent as we start to work through this. Now what we're going to do is we'll look at our first filter. So this is a low pass filter, but it's not an active filter, it's just a passive filter, meaning there's no gain stage involved in it. So we'll analyse this in terms of the time domain, and then we'll analyse it in terms of a complex frequency. So in terms of the time domain, we can see that voltage here, V in, is a volt drop across the resistor plus a volt drop across that capacitor. So the volt drop across the resistor by Ohm's law is just the current at time t times the resistance, and the volt drop across the capacitor is given by 1 upon c, the integral I of t by dt. So we've gone over this equation here in a previous video when we talked about capacitance and inductance. So you can have a wee look at that previously if you're unsure of it. So if we were to convert this into the complex frequency domain, we would have Vi of S, we just replace our t with our S, equals I of S times R plus I of S upon SC. Now it's upon SC because in the complex frequency domain, integration becomes a division by S. Again, we've seen that in a previous video. So what we can do now is we can take out our common factor of S, or I of S, which will leave us with our R plus 1 upon SC in this side here, and we're actually now seeing the use of the complex frequency domain, because up here we had an integral equation, but at this point here we no longer have an integral equation. It's simply an algebraic equation. There's no integrations or differentiations in this complex frequency domain. So what we can do then is we can take the common factor of SC. That will give us RSC plus 1. So this gives us the value for the V in as a function of the complex frequency S. That's this thing here. Now V out is just going to be given by what we have above here. It's just the IS upon SC. It's just the volt drop across that capacitor there, which we defined up here. Now what we're going to do is we're going to look at the gain of the system, so it's the voltage gain of the system, but it's a complex valued function, meaning it's got a magnitude, an amplitude, and it's got a phase associated with it. So we're going to have V out as a function of S, which is this term here, divided by V in as a function of S, which is this term here. So we divide both of those out. The IS cancels the IS. We're dividing by this part here, so it's the same as multiplying by the reciprocal, so the SC will cancel with SC, and you'll simply be left with 1 upon RCS plus 1. Now this complex value here, we're going to replace it by just a single value, and we'll call it G of S. Now that G of S is our transfer function. Okay. Now if we want to look at this transfer function, but we want it simply in terms of not of a complex frequency, but just as a simple frequency, we can replace the S with a j omega. So now we have our G of j omega equals 1 upon j omega RC, and this is going to be the frequency response of our system. Okay, so wrapped up in this we have a magnitude and also a phase. So we'll look at it first of all in terms of a three-dimensional picture of it. So what we would have is a frequency along this axis here, and then we would have a real part of our complex frequency and our imaginary part of a complex frequency. And in this instance here, it looks like a low pass filter, and what it would be doing is we would in effect have, if we could split this into axis into little phasors, we would see the little phasors starting to rotate round the axis as shown here. But it means then that because this is a phasor rotating around the axis, this phasor is going to have a magnitude. Now the magnitude is this length here. Okay, now that length there by Pythagoras is going to be the real part squared plus the imaginary part squared, and we take the square root of it, will give us this length here. It's kind of like taking all these little phasors and rotating them back round on the axis, okay, or rounding the until they sit on the real axis, okay, and they'll all have this length, these lengths here, okay. So this here is our value of our g omega. So this is the magnitude, and we say it's a magnitude because you've got the two little lines, one either side. So this is a magnitude plot. So it's magnitude against our frequency, and then of course we have to include the actual phase as well, so the angle that these are actually sitting at. Now we include that phase using the phase plot there, so we have an omega along this axis and we'll have a phase along that axis which can range from plus, and in this case here there's only one element that can change the phase, and that's one capacitor, so it's only going to change from plus or minus 90 degrees. So in this instance the capacitor is going to be minus 90 degrees. So this is the phase response here. So don't get confused, these two drawings here just represent this one drawing here, and we do this here because it's hard to see what's going on. If you try to imagine what's happening in 3 dimensions, it's much easier to draw it out and work with it in 2 plots in simply 2 dimensions than 1 plot in 3 dimensions. Okay, and we've noted down here that the magnitude of this g omega is the real part of the signal squared plus the imaginary part squared, and take the root of it. Okay, gives us this distance. So if we want to find the actual amplitude response given by a particular transfer function g of j omega, then in this instance here the magnitude is going to be g of omega equals, well, it's going to be the magnitude of v out upon v in, which is the magnitude of our transfer function, which is 1 upon 1 plus j omega. And what we can do is we replaced the RC with the value tau. Okay, so RC is if we multiply it and we looked at it, you find that RC was actually a time value, so the value of time, so a time constant. So we just replace that with a value tau. So if we were to work out this magnitude, we would have to take the square root of everything, but then we'd have to square each of the terms. So 1 squared would be 1, and 1 squared would be 1. Of course, the square root of the top line would just give us 1, and we'd have the square root of the bottom line, and it would just be the omega t here squared as well. Okay, so the magnitude is just going to be given 1 upon root of 1 plus omega t squared. Now, as I said, the Bode plot was just a way of doing the magnitude to the frequency and the phase to the frequency, but we just changed the scales and the axis. Okay, so we'll see that in the next page. Okay. So what we have is the magnitude g of omega, but we have the magnitude in terms of decibels. Okay, now in this instance here there's a gain, there's no gain, so in fact there's a gain of 1. Okay, so it means that the actual magnitude, the actual value of the decibel is going to be 0 dBs, and then it's what's going to happen is that as the frequency increases, we hit a cut-off point, and that we start to get a signal loss. Okay, so there's never any real gain, it's just if you like, a negative gain. So we're going to draw first of all, we're going to have an amplitude response and a phase response. So we're interested in looking at both of those. So the amplitude response is drawn here. So we've got our g of j omega up that axis, and along that axis there we're actually going to use the log of the frequency. Now what we'll do is we'll do it in terms of our frequency divided by the value of tau, okay, because it makes it a lot simpler and easier when it's drawn out. So we're going to have a value of 0.01 tau, 0.1 tau, there's 1 upon tau, 10 upon tau, 100 upon tau, 1000 upon tau, okay? And you can see here that when omega is equal to 1 upon tau, then our transfer function there, our magnitude of the transfer function, g of 1 upon tau, is going to equal 1 upon the root of 1 plus 1 upon tau times the value of our tau, all squared, which is going to give us our 1 upon root 2. So the gain when omega is 1 upon tau is 1 upon root 2, which in terms of dB is going to be 20 log to the base 10 of 1 upon root 2, which is minus 3 dB. So the frequency omega is 1 upon tau is called the 3 dB cut-off point, and it marks the edge of the passband. So the edge of the passband is going to occur when the output power drops by a half. That is a half power point, which is minus 3 dB, is going to occur when the voltage is reduced by a factor of root 2. It's by a factor of root 2 because power is related to voltage squared. So it's not really directly to voltage but to voltage squared, so that's how you get a factor of root 2 there. Now we will become using this again, so if you're unsure of it you can have a read over it again, or print out the notes and have a look over it, but we will be using it in other videos, so you'll soon get used to seeing these. Okay, so let's look and see what happens whenever we go further up the frequency band here. So if we consider looking at a value of the frequency omega, which is much greater than 1 upon tau, so really it's a high frequency. So we're saying omega tau is much greater than 1, so that magnitude g of omega, well, if omega tau is much greater than 1, then we can kind of forget about that value of 1 because this is this omega tau dominates. So we have 1 upon the root of omega tau squared, so that equals 1 upon omega tau. So let's see what happens when we take a couple of values for omega. So if we have the gain in dBs, so for some value omega 1, well, it's going to be equal to 20 log to the base 10 of the 1 upon omega 1 tau. Now if you remember your logarithms there, that's going to be equivalent to our minus 20 log to the base 10 of omega 1 minus 20 log to the base 10 of tau. Now if we consider a second example for omega, so we have omega 2 equals say 10 times omega 1, then we'll have our gain in dBs of omega 2 would be 20 log to the base 10 of 1 upon omega 2 tau, which will equal minus 20 log to the base 10 of omega 2 minus 20 log to the base 10 of tau. So that's going to equal minus 20 log to the base 10 of, now omega 2 in this case here is going to be 10 times omega 1. So again from logarithms that's going to be equal to minus 20 log to the base 10 of omega 1 minus 20 log to the base 10 of tau. So we've already worked out this term here is going to be a value of minus 20, and this thing here, the rest of it here, is going to be the gain in dBs of our value of omega 1, which is just this full section here. Okay, so it's a bit of a mouthful, and if you're not used to your logarithms it might look a bit confusing, but the upshot of it really is, what it's telling you is that as the frequency rises by a factor of 10, then the amplitude is going to decrease by a factor of 20 dB. So it's going to be a straight line decrease of 20 dBs, okay, and a factor of 10 is called a decade. So we get a decrease in the output at high frequency of 20 dBs per decade, and that's a little proof of it. Not a proof that you tend to remember, but if you've seen it once you know where it comes from. Okay. Now if we look at the other side, if we think about omega as a small value, so it's much less than 1 upon tau, then you can say that g of j omega is 1 upon 1 plus omega tau squared. So if this is very small compared to the 1 at 10, then the 1 dominates. So that equals 1 upon the root of 1, which equals 1. So it's just saying that the gain of that is going to be 1 or 0 dBs. So that's us looked at the amplitude response. Okay, at low frequency it's going to have a 0 dB gain, and there's going to be a cut-off point at minus 3 dB, so that's the edge of the passband, and beyond that the value is going to decrease at 20 dBs per decade. Okay, and that's just what we've seen in the previous drawings. Okay, so that's the amplitude response. Now, what about the phased response? We'll go and we'll have a little look at that next. Okay, now the phase response here, I've attempted to draw it out in 3 dimensions. Okay, so I attempted to draw out, the low pass filter in 3 dimensions, and from this we'll be able to pick out the phase response. So we've said before that what we have is this transfer function here. So we've got omega along that axis, imaginary value along that axis, and the real value up that axis. So the transfer function there is going to look like some rotating phasor as it rotates round here. You can see it, and it rotates in the opposite direction along this axis. So in order to get the real part of this transfer function, we would have to look in from this angle. So imagine standing here and looking in from this angle, or shining a torch there, and it would project the shadow of this onto this axis here, and that shadow you would get would be the real part of this complex function. And also, if you were to come from above and look down, and again shine a torch down, and we were to look at the shadow of this function from the top down to the bottom, then we would see the imaginary part of this function, and it would look something like that. Okay, now I do have another course on the Fourier and Laplace transforms, and it goes into detail in this, and also it does the drawings of this, the printouts in MATLAB, so you can see it physically happening in 3 dimensions as you move round about. Okay, so it's well worth to having a look at that. So now we know that we don't represent it like this. We know we represent it in terms of a magnitude. That's our magnitude of g omega, which are these lengths here, and also a phase, and the phase is the angle. Okay, now the phase response here is defined as going to be the inverse tan of the imaginary part of our function divided by the real part of our function. And you can see that here, if we had some function here, we had a phasor, say sitting at a particular angle here. Well, the angle in here is going to be the inverse of the imaginary divided by the real. So it's inverse tan imaginary divided by real. Okay. So for a low pass filter, we can see that we're going to have our response here, g of omega is 1 upon the root of 1 plus omega tau squared. So this is equivalent to saying, well, if we look at that, it'd be 1 at an angle of 0 minus the tan of, now we're going to have the bottom line here, it's going to be our omega tau divided by the real part of it, which is 1. Okay, so that whole thing there is just going to be minus tan of omega tau upon 1. So if we were to say omega equals 1 upon tau, then we would say that equals minus tan of the value omega would be 1 upon tau, so that would be tau upon tau, which would just give us a value of 1, so that would be the minus inverse tan of 1, so that's going to be minus 45 degrees. Okay, so now as omega tends towards 0, the phase is going to be 0. Okay, and also when omega tends towards infinity, when omega is large, then the phase is going to be the tan of a large angle, the tan of a large value, which is going to be 10 towards minus 90. Okay, so it means the phase response is going to look something like this here. Okay, and that's as expected because that's a capacitive circuit. Okay, so that's all there is for the theory behind Bode plots. We'll go and the next video and we'll go and look at an actual example of a Bode plot. Now, if you really are interested in all the theory of this and the in-depth mathematical description and a good graphical description, my other course on the Fourier Laplace transform does cover it. I know I'm kind of blatantly trying to sell it here, but it does actually cover the stuff in detail. Okay, so thank you for listening and goodbye.